This diagram represents an object being thrown at an angle. We call this object a projectile because the only thing that influences it once it's released is gravity. We're going to assume no air resistance. That throws a big wrench into things. In the absence of air resistance, the only force acting on this object is gravity. It's a projectile, and it follows a path that looks more like this. Does anybody know the shape of that path? Does anybody know what that's called? It's funny because we were talking about that a little bit earlier today. It's a parabola. Now, in this parabola that shows the motion of the object, of the projectile that's moving through the air under the influence of gravity, we can see that we have two components. We can see that we have an x component. It's moving to the right, but it's also moving up and down. So there's a y component to it as well. What I want you to see here first is the x component and the relationship between x component of velocity and time. This is the initial x component of the velocity. That x component of the velocity does not change throughout the whole problem. And the reason that it doesn't change, the reason that the x component of the velocity remains constant through the whole thing is because there are no forces acting on this object horizontally. There's nothing to cause it to speed up or slow down. So if it was moving at 5 meters per second horizontally, there's nothing to cause it to move at 4 or nothing to cause it to move at 6. It will move at a constant velocity of that 5 meters per second for the whole trip, horizontally. But vertically, there is gravity. Vertically, gravity will cause this object to initially slow down as it goes up into the air. So we're going to say that the initial y component of the velocity looks like this, and then it looks like this, and then it looks like this, and then it becomes, what's the y component up here? 0. And then it becomes like this, and then it becomes like this, and then it becomes like this. So the x velocity remains constant velocity. The y component of the velocity decreases in velocity and then increases in velocity. In other words, the x component is uniform motion or constant velocity, and the y component is, what's one word to describe it? Starts with an A? Acceleration, right. Now, if that's the case, if the x component can be described by constant velocity and the y component can be described independently of the x component, okay, x component and y component don't affect each other in the slightest. If the x component can be described independently of the y component, then the x component can be described by a group A equation. V is equal to delta D over delta T. Think about that. If it's moving at a constant velocity horizontally, then why wouldn't we describe it using V is equal to delta D over delta T? And it would move at a constant velocity horizontally in the absence of air resistance. Now the y component, well, that's a group B problem, right? Because it's accelerating. There's a number of group B equations that we have at our disposal on our data sheet, but there's one equation that I always want you to try first because it's the one that's going to work the most often. Start off with this equation. D is equal to VIT plus 1/2 ET squared. There's a reason why this equation ends up working most often for the y component. This equation, D is equal to VIT plus 1/2 ET squared, really is the equation for a parabola. And it's a parabola that we have for a shape here. So it's not a coincidence. It's not a coincidence that D is equal to VIT plus 1/2 AT squared is the most useful equation to describe the y component here. All right. Now, strategically, how do we solve a problem involving projectile motion? We see that we have two equations up there. D is equal to delta D over delta T, and D is equal to VIT plus 1/2 ET squared. I'm telling you right now, written response question number 1 on your diploma exam is a question like this. Written response number 1, not on your diploma exam, on your final exam, is like this. You will, or at least you better, start that question off by writing down these two equations. You don't even have to know where you're going with it after that. It always starts like this. But what do we do with it? Well, the strategy after we write down these two equations is, it kind of seems odd, but just sub in numbers and see what happens. Don't try to solve for anything in particular. Just sub in numbers and get something. Try to get something. Don't worry about what it is. Eventually, what you're looking for will just kind of fall into place. Let me demonstrate that with an example here. This one says a ball is rolling at 10 meters per second on a flat roof 15 meters above the ground, and it rolls off the edge. How far will the ball land from the edge of the building? Here's the building. Here's the ball. The ball is moving with a horizontal velocity of 10 meters per second. Now, what's the shape of that ball's path going to look like? It's going to look something like this, right? Is that a parabola? Well, it's a half a parabola, right? Hey, does that make sense? It's a half a parabola. So while the ball is undergoing projectile motion, it is a parabola. It just doesn't undergo projectile motion as much as the last one did. That's okay. Actually makes it easier. Now, we also have a height of this building. It's 15 meters, so let's label that as well. And we're looking for this value right here, this distance right here. How far from the edge of the building does this thing land? Let's analyze the x component now. The x component is described by which equation? Always. It's got to be this one. It has to be. Because it's constant velocity, it has to be v equals delta d over delta t, yeah. And now let's write down the other one. Again, we don't even necessarily have to know exactly where we're going with this. This is one of those types of problems where we just do something the same all the time, and then just brute force plug in some numbers and see what happens. Do we know what v is for the x component? Yes, what is it? 10 meters per second. That velocity is all horizontal, right? None of it's vertical. So we're going to say of that 10 of it is x component. Now, do we know what the horizontal displacement is? That's what we're looking for, isn't it? That's the horizontal displacement. How far from the base of the building does it end up landing? We don't know what that is. We don't know what time is either. So that wasn't particularly helpful to sub in that 10. That's okay. We didn't necessarily have to recognize that. We just sub it in and, oh, we got two unknowns. Oh, well, let's move on to the next equation, see what happens. Do we know what delta d is for the y component? 15, close. Close. Negative 15 because it ends up below where it started, right? 15 down. Do we know what vi is for the y component? 0. That 10 meters per second was all x component. Now, if you had this problem, and we'll deal with this tomorrow, something like this where it's launched at an angle, vi for the y component wouldn't be 0, right? We'd have to find x and y components of the initial velocity. But for this one, vi for the y component is 0. Now, 0 times time, whatever the time is, this gives me 0. It's 1/2 of, what's a? Vertical, a, acceleration. Negative 9.81 meters per second squared times t squared. Now let's simplify this a little bit. Half times neg 9.81 is neg 4.905. And now let's say negative 15. Negative 15 divided by negative 4.905 gives me a value of 3.0581 t squared. And then we're going to square root that. We get 1.7487 for time. 1.7487 seconds for time. Do you notice that we weren't looking to solve for time? We were looking to solve for horizontal displacement, right? But we weren't trying to solve for that. We just solved for whatever happens to come out of it, and it happened to be the time. It's not my final answer, so I'm going to write it down as an unrounded number. What am I going to do with it? What am I going to do with it, Evan?
Put it in your other equation.
I'm going to put it into here. So my equation now becomes, for x, 10 is equal to delta d over 1.7487 seconds. And then delta d, take the 1.74 out by multiplying, delta d becomes equal to 17.487 meters, which is 17 meters. So this ball lands 17 meters from the edge of this cliff. Does that make sense? Why was it, answer this question for me, please. Why was it that I had to be very sure about my x and y velocities? 10 for x, 0 for initial y velocity. Why was it that I had to be sure to distinguish between x displacement and y displacement? Why was it that I didn't care for time? Time, I got it for y, and then I subbed it into x. Yeah, whatever, that's fine. How come? Because time's a scalar. Velocity is a vector, displacement's a vector, x and y components matter, right? But for time, it's a scalar. It doesn't really matter whether you're using it for x and y. In the end, it's in the air for the same amount of time vertically as it is horizontally. Does that make sense? Okay, we're not going to give you any homework with this tonight. You do have a unit assignment due on Tuesday that's in preparation for your test on Thursday. My suggestion, since you don't have any homework tonight in Physics 20, is take a peek at that unit assignment. It's on Google Classroom. You can print it and do your work right on there, or you can just do your work on a loose leaf and head it in that way. That's fine. But most of those questions you can now do, with the possible exception of a couple of questions that relate to projectile motion here. We'll pick this up tomorrow. We'll do a couple more examples and give you some problems to work on with this tomorrow as well. All right, that's it for tonight.